In this video, we will be discussing various types of chemical formulas and the types of bonding that can occur. We can categorize the various compounds in terms of the types of bonds that are involved in holding the atoms together. There are three general types of bonding that we will consider. So the first type is ionic bonding. In ionic bonding, we have electrostatic attractions between cations and anions. The term electrostatic is referring to the static electric charge, the non-moving charge on the ions. So generally, a positive ion will be attracted to a negative ion. In this case, we always write the formula so that the cation comes first and then the anion. Usually the cation will be a metal of some sort, a metal cation, although it can be some sort of grouping of nonmetals as well. And there's one important example of that, and that is the so-called ammonium ion. In the case of the anion, we also can have monoatomic anions, but there are some cases of polyatomic ions that we'll consider in a moment. We can also have covalently bonded compounds. These are usually comprised of all nonmetals in the formula. We will often use subscripts to indicate how many of the atoms there are in the formula, with the caveat that we have to be very careful about looking at the atomic symbols. So for example, Cl2 is the formula for elemental chlorine. It's one of the diatomic elements. This is not a carbon and two iodines. That is not a reasonable formulation for a carbon-containing compound. We could also have slightly more complicated molecules where we'll have to learn why the atoms are attached together the way they are. But for example, butane has 4 carbons and 10 hydrogens in the formula. And then finally we have metallic type bonding, and these are generally elements that are metals. We would write the formula as just the single atomic symbol, although in fact these solids are comprised of many, many atoms. They don't necessarily form discrete molecular units. And so sometimes we'll have alloys. Usually when we write the formula for an alloy, we write the symbol for the most abundant element in the alloy. So something like brass would be primarily copper. When we write the formulas for ionic compounds, we sometimes will need to take into account that the cations and anions can either be monoatomic or possibly polyatomic. When we write these formulas, we typically will group together the cations and write them first, and using subscripts to indicate how many of the cations there are in the formula. And then finally, we will also indicate how many anions are present with a subscript as well. This is relatively straightforward when there are monoatomic cations and anions in the formula. So, for example, we could see formulas such as NaCl, where there's 1 sodium and 1 chlorine in the formula. This is the so-called formula unit, and this is repeated many times in the solid. Likewise, we could have something like iron 2 oxide, shown here, FeO. The ratio of iron to oxygen is 1:1. There is no subscript written. It's implied that there is a subscript of 1 just to the right of the iron and the oxygen. If there's more than one of the various ions, then we need to use subscripts. So, for example, Fe2O3 indicates that there are 2 irons and 3 oxygens in the formula, giving the ratio of 2 to 3. A further example is something like potassium sulfide, where there are 2 potassiums and only 1 sulfide, the 2 subscripted to the right of potassium. But again, for the sulfur, it's implied that there's just 1. If we have polyatomic ions, then we have to, in certain cases, include parentheses if there is more than one of the polyatomic ions. Some examples here, we have calcium carbonate. In this case, calcium is the positively charged ion, and there's only one of the calciums, whereas carbonate is a group of 4 atoms, 1 carbon and 3 oxygens. And so in this case, since there's only one of those ions, we don't need a parentheses. So in this case, the charges are of the positive ion and the negative ions are the same. If we have something like ammonium sulfate, in this case there are 2 of the ammoniums. The subscript 2 is outside of the parentheses. The ammonium ion itself is comprised of 1 nitrogen and 4 hydrogens. And so in this case, in this overall formula, there would actually be 2 nitrogens and 8 hydrogens in the formula, where the 2 is distributed and multiplied by the appropriate numbers inside of the parentheses. The sulfate, there's only one of the sulfate, so there's 1 SO4 unit, which is the anion. And then as our final example, we have iron 3 sulfate is the name of this compound. We'll talk about naming shortly. But in this case, there are 2 irons and 3 of the sulfates, with the 3 outside of the parentheses, and sulfate being comprised of 1 sulfur and 4 oxygens. So in this formula, there's actually 3 sulfurs and 12 oxygens. If the formula is comprised of all nonmetals, quite often we will consider these things to be discrete units that are made up of more than one of the elements in the formula, and so we refer to these as molecules. There will be strong bonds holding the atoms together to form the molecular unit, and then less strong interactions between the various molecules. And we will talk about the difference between intramolecular versus intermolecular forces shortly. So right now we're just going to focus in on the bonds within the molecule, the intramolecular forces. So in this case, these are covalent bonds. Examples of molecular formulas, we might have something like water, H2O, 2 hydrogens and 1 oxygen. Again, in this case, if it's implied that there's only 1 oxygen, we don't write the 1. We also have something like elemental oxygen, which is O2, or ozone, O3. But then we could have things like carbon dioxide. Carbon is further to the left than oxygen, so you would write that first, and then the oxygen, and so there's 1 carbon and 2 oxygens. Carbon monoxide, 1 carbon, 1 oxygen, and then finally we have methane, which is got a unique name because it's an organic compound. We wouldn't typically call this a name like carbon tetrahydride, or that is a possibility, but would be unusual. So, but methane has 1 carbon and 4 hydrogens. We need to know the difference between the so-called molecular formula and the empirical formula for a particular compound. Turns out the molecular formula tells us exactly how many atoms there are in the molecular unit, whereas the empirical formula tells us the lowest whole number ratio of atoms in the molecule. And so for examples, okay, we have 4 compounds here: water, ethene, acetylene, and benzene. ethene, acetylene, and benzene are organic compounds, so the names are a little strange. But water's molecular formula is H2O, and in fact, in this case, that is also the lowest whole number ratio between the atoms, so it's also the empirical formula. Ethene has got a molecular formula of C2H4, but in fact, both the 2 and the 4 can be divided by 2 to lower that ratio to end up with an empirical formula of CH2. Acetylene has a molecular formula of C2H2, which both of the 2's can be divided by 2. So in this case, the empirical formula is just CH. And then finally, benzene is C6H6. Interestingly enough, the empirical formula for benzene is also CH. So both acetylene and benzene have the same empirical formula, but different molecular formulas. We also have other ways to write formulas to give further information about how the atoms are attached to one another to form the molecular unit. So sometimes you will encounter these so-called structural formulas. Structural formula is somehow necessary to give an idea of how the atoms are attached, but also can give further information about the three-dimensional shape of the molecule. So, for example, if we consider a molecule like methane, CH4, it turns out that carbon is in the center of this particular molecule, and there are 4 hydrogens that are attached to it. In the structural formula, we use lines to attach the atoms to one another, and these are representing bonds. So, now, the problem with the structural formula shown here is that it looks like it's a 2-dimensional shape where carbon is in the middle of a square formed by the hydrogens. And in fact, this is not the shape of methane. We can also then give some sort of indication of the shape of the molecule by using a perspective drawing that includes wedges and hash marks that indicate that the wedge has got the atom coming closer to us and the hash mark is going further back. So in fact, methane adopts a structure that we describe as being tetrahedral, where all of the angles are approximately 109 degrees. We sometimes can write the structural formula as the so-called ball and stick model, which gives us some idea of the relative sizes of the atoms along with how they're attached to one another. And then finally, sometimes we use space-filling models to also give some idea of how big the atoms are with respect to one another. As the number of atoms in the formula increases, the complexity of the structural formula can also become quite a bit daunting, so to speak. So if we consider methanol, for example, which is still a relatively simple molecule, in this case, we could write the formula as CH3OH. In this case, we see that there's a carbon, and it's implied that the hydrogens, there are 3 hydrogens attached to that carbon. In addition to this carbon, we will learn that carbon always has 4 things or 4 bonds attached to it. So carbon is also attached to the oxygen, and the oxygen also then has a hydrogen attached to it. So we can also write the formula of this compound as CH4-1, but this doesn't really tell us much about how the atoms are attached, and you might even think that all 4 hydrogens are attached to carbon, and that doesn't really make very much sense in terms of having the oxygen and how that might be attached. So we could write a structural formula like this, where there's a carbon and 4 bonds attached to it, 3 of them to hydrogen, 1 to oxygen, and then a hydrogen also attached to the oxygen. We could have more of a structural formula. It gives more of a three-dimensional sense of how these things are attached. And then finally a ball and stick model with some color to indicate the different atoms and